function. Just looks like that. Now, if I'm going to reverse something, I'm going to take some segment and then flip it. So that one reversal threw me to a picture that looks like this. Okay, it's a plot of kind of thinking of the permutation as a function from n to n. So why should there be n plus 1 choose 2 minus n of these? Well, we have two positions to choose. This one and this one, right? There's n plus 1 choose two ways to choose those. But in n of the cases, these are right next to each other. So in n cases, it'll actually look like this, and then these two will be right next to each other. And then we'll have an increase after that. And of course, we've already counted this. These are just increasing permutations. So that's why this should be n plus 1.
Equals n choose n.
Well, of course, but I wanted to write it this way. Okay, so I thought, well, we can just continue this process, right? We can choose something to flip. So if we wanted to do two reversals, well, we could flip something in the first bit, and then we would have an increase, a decrease, an increase, and then a decrease and an increase. Or, of course, we could flip something in the first segment together with the second segment. And then we have our initial increase, and then we have this, which has become an increase, but a bigger increase. And then this. And it was about this point that I gave up on this, doing this by hand. And this is why I taught Shalosh to do this, okay? So what Shalosh can do is he can take these pictures, which I call grids, and it can compute all of the grids for sorting by 2 reversals, or 3 reversals, or 4 reversals. You know, Shalosh doesn't get bored, although he runs out of computer time. So starting at about 7 reversals, Shalosh keeps up himself. So for 2 reversals, you get 6 of these grids, I think. For 3 reversals, you're up to 45. And for 4 reversals, you're up to about 600. Okay, so once you've got these grids, the question is, could we count them like this? And so indeed, Shalosh can figure this out. This is not an easy problem because when we have these grids, there are permutations that are in multiple grids. Okay, so for instance, we had our 2 grids to be, so this, and this, then we have to be a little bit careful because they have a non-trivial intersection. Okay, but again, this is something I wouldn't want to do, but Shalosh is perfectly willing to do. Okay, so that's all I want to do is announce. I don't have a theorem to state, but I have a maple to state. So there is now a package. Which for fixed k will output, and actually, so this is always a polynomial and it's always of degree 2k. Polynomial with degree 2k, counting these permutations. Okay. And the other nice thing about having Shalosh do this is that there are other operations. There's not just reversals, there are things called block interchanges and all kinds of other operations. And Shalosh is perfectly happy to consider doing, one reversal and then a block interchange and then another reversal after this, whereas human mathematicians aren't really willing to consider that because it gets really complicated really quickly. Okay, so in the interest of getting us back on schedule, I'll stop there. Okay.
Is it obvious this 2k?
It's obvious that 2k is an upper bound of the degree, right? Because you're choosing 2 indices each time.
So in order to program it, you have to be clever, right? You have to spend a few hours to teach Shalosh how to do these grids and how to.
Yeah, I did.
So you needed Vince to do it.
I didn't need Vince to
So I have a better way of doing it for k up to 4 and possibly 5. That's
just
actually counting.
We have then we need a theorem saying that it's actually a polynomial and it's not just bounded by a polynomial. Right?
Oh, you don't know it's a polynomial, by the way.
You don't know that it's a polynomial, but yeah.
But you don't know it's a polynomial.
But you know that it grows at most as
polynomial.
fast as a polynomial degree.
Oh, so 2k is not upper bound for degree. It's not obvious to Shalosh here that it's a polynomial.
Right, it could be a quasi-polynomial.
How bad is the next polynomial?
Well, I mean, it's got, end of the, some coefficient of n to the 4th, and so on. So I've kind of looked for patterns, and I haven't found anything. That they don't look like natural, nice polynomials.
Is there a chance that this polynomial is the Eckert polynomial of some simple polytope?
That would be really interesting if it were.
It is for n choose 2.
Most of them are more complicated than.
Yeah, the next case is more interesting.
Any questions? All right, thanks. Next talk will be in 5 minutes.
It's like every day you forget.